All right, so we continue to look at question 2. Now, question 2 says a parallel plate capacitor has square plates whose sides are 250 millimeters long. So the length of the sides is 250 millimeters. Of course, you convert that to SI units, which is found by dividing by 1,000. We'll get 0.25 meters, right? And which are situated 1.5 millimeters apart. So therefore, the separation of the plates D is 1.5 millimeters, or 1.5 times 10 to the minus 3 meters, right? They want us to calculate the capacitance of this capacitor when the material between the plates is A, air, and when the dielectric of relative permittivity, 2.4. Now, when it comes to a parallel plate capacitor, where the area of the plates is A and the separation is D, and there's air between the plates of the capacitor, then the formula for the capacitance is given as C equals epsilon naught A over D, where of course epsilon naught is the permittivity of free space and has the value 8.85 times 10 to the minus 12 farads per meter. Good? So having done that, we can basically, first of all, we need to calculate the area of the plates. So the area of the plates is given by, so A, since it's a square, then it's basically side by side. So it's a square of length 250 millimeters or 0.25 millimeters. So this gives us 0.25 meters times 0.25 meters, which gives us 0.0625 meters squared, right? So 0.25 squared, let me just check to make sure my math is correct. So 0.25 squared, right, 0.0625 meters squared. And so therefore the capacitance C is equal to epsilon naught A over D. This gives us 8.85 times 10 to the minus 12 times area of 0.0625 divided by the separation of the plates 1.5 times 10 to the minus 3. And this gives us, let's work it out. So we have 0.0625 times 8.85 exponential negative 12, and then divided by 1.5 exponential negative 3. So this gives us a value of 3.69 times 10 to the minus 10 farads. So therefore the capacitance of this capacitor is 3.69 times 10 to the minus 10 farads. Right? So that is with air between the plates of the capacitor. Now, whenever there is some dielectric material between the plates of a capacitor with relative permittivity R, then basically the formula becomes this. We have C equals epsilon A over D, where of course epsilon is called the absolute permittivity of the dielectric. So epsilon is called the absolute permittivity of the dielectric and is given by and is related to the permittivity of free space by the equation E is equal to the relative permeability epsilon R times the permeability of free space. So in this particular question, we're given the relative permittivity of the dielectric material and the relationship between the relative permittivity epsilon R, the absolute permittivity epsilon, and the permittivity of free space epsilon naught is this equation, right? Which basically stems from the fact that epsilon R is equal to the ratio of the permittivity of the particular dielectric divided by the ratio of the permittivity of the material to the permittivity of air, right? So therefore, what this means now is that our formula becomes C is equal to epsilon R, epsilon naught, A over D. But if you compare this formula to this one, essentially all we're doing is multiplying the capacitance of the capacitor with air between its plates by the relative permittivity of the dielectric material. So since you already found the capacitance in part A with air between the plates, we can simply multiply this value by the relative permittivity. So therefore this now becomes C is equal to 2.4 times 3.69 times 10 to the minus 10. And that gives us 8.85 times 10 to the minus 10 farads. Alright, so therefore with a dielectric of relative permittivity 2.4 between the plates of the capacitor, the capacitance has basically increased to 8.85 times 10 to the minus 10 farads. Now that was question 2 from our worksheet. Now, let's look at question 3 from our worksheet. Now, question 3 says, two 15 microfarad capacitors are connected in parallel, and the pair are connected in series with a 45 microfarad capacitor and a battery. The PD across the parallel pair is 30 volts, and we're asked to make a few calculations. So first of all, let's represent the diagram or the situation on a diagram, right? So let's basically draw the circuit to represent the situation. Right? So we have two 15 microfarad capacitors are connected in parallel, and the pair are connected in series with a 45 microfarad capacitor and a battery, right? So the two 15 microfarad capacitors are connected in parallel. So this is 15 microfarads, 15 microfarads. And the pair are connected in series with a 45 microfarad capacitor, right? And of course, the entire combination is of course connected to a battery. Right? We're also told that the PD across the parallel pair is 30 volts. So the PD across the parallel pair is 30 volts. Let's call that VP for parallel is 30 volts. Right? And what we're asked now to calculate in part A of the question, we're asked to calculate the charge stored on each capacitor. So let's proceed. Now let's first look at the parallel branch. So for the parallel branch, now because these capacitors are connected in parallel, it means the PD across each of them will be the same, right? So the PD across each resistor or each capacitor rather in the parallel branch would be 30 volts. So we can say that for each of these capacitors, then the capacitance C is equal to 15 microfarads and the PD V is equal to 30 volts. And using our formula, Q is equal to CV, then this gives us 15 microfarads times 30 volts, which gives us 450 microcoulombs, right? So 450 microcoulombs, which of course is the same thing as 4.5 times 10 to the minus 4 coulombs. So each of the 15 microfarad capacitors in the parallel branch will store a charge of 4.5 times 10 to the minus 4 coulombs, or 450 microcoulombs. Now, because they're connected in parallel, the total charge stored on these capacitors will be the sum of the individual charges stored. So therefore, the total charge stored so 450 microcoulombs times 2, that will give us 900 microcoulombs, or we can write it as 9.0 times 10 to the minus 4 coulombs. So this would be the total charge stored on these two capacitors connected in parallel, right? Now, because the two capacitors are connected in parallel and that combination is connected in series with the 45 microfarad capacitor, it basically means that the total charge stored by these two capacitors must be stored by the 45 microfarad capacitor. Now, we know that basically whenever capacitors are connected in series, they store the same charge. So essentially, these two 15 microfarad capacitors connected in parallel are equivalent to a 30 microfarad capacitor. Because we know that when capacitors are connected in parallel, we tend to treat them like resistors in series and add their values. So 15 plus 15, 30 microfarads. So essentially, this is like a single 30 microfarad capacitor connected in series with a 45 microfarad capacitor. This 30 microfarad capacitor will store 900 microcoulombs, or 9 times 10 to the minus 4 coulombs of charge. And therefore, because this 45 microfarad capacitor is connected in series with it, therefore must store the same amount of charge. So therefore, each of the 15 microfarad capacitors will store this amount of charge, 450 microcoulombs, or 4.5 times 10 to the minus 4 coulombs, and the 45 microfarad capacitor will store a charge of 900 microcoulombs, or same thing as 9.0 times 10 to the minus 4 coulombs, right? So that is part A of the question. Now let's look at part B. Now part B wants us to find the EMF of the battery. Now again, we know that these two capacitors are connected in parallel and the PD across each of them is the same, and that is equal to 30 volts. We were able to calculate the charge stored by the 45 microfarad capacitor, and therefore this will allow us to find the PD, let's call that V, across its plates, right? So using our formula, C is equal to Q over V. Then from that we can get that V is equal to Q over C. So therefore the PD across the plates of this capacitor will be found by dividing its charge stored, or the charge stored by its capacitance. And so therefore V is equal to 900 microcoulombs divided by 45 microfarads. And this gives us 20 volts. So the PD across the 45 microfarad capacitor is 20 volts. And what this therefore means is that the battery voltage, or the battery EMF, so the EMF E of battery is equal to the PD across the parallel branch plus the PD across the 45 microfarad capacitor. So this gives us 30 volts plus 20 volts, which of course is equal to 50 volts. So what we have in the circuit is essentially a 50 volt battery, right? Now part C wants us to find the total capacitance of the circuit. Now once again, we said that whenever capacitors are connected in parallel, we essentially treat them like resistors in series, and so we add their capacitances similar to how we would actually add the resistances of the resistors in series. Similarly, when capacitors are in series, we treat them like resistors in parallel, but so we do not add the capacitances, but we use the formula 1 over CT equal 1 over C1 plus 1 over C2 plus 1 over C3 and so on, right? Similar to resistors in parallel, of course, if it's just 2, then the total effective capacitance will simply be equal to the product of the capacitances divided by the sum of the capacitances. So in this particular case, because we have two capacitors essentially we have a 30 microfarad capacitor, because again these are in parallel, so we just add them. So a 30 microfarad capacitor is in series with a 45 microfarad capacitor, and therefore we can say that the total capacitance CT is equal to 30 times 45 divided by 30 plus 45. And this gives us, that's 450 times 3, that's 1350 divided by 75. And what does that give us? That gives us 18 microfarads, right? So this gives us, yes, this gives us 18 microfarads. So what this basically confirms is that whenever we connect capacitors in parallel, then series rather, the effective capacitance is always going to be smaller or less than the smallest capacitance in the circuit, right? So essentially, connecting capacitors in parallel will result in an overall reduction in the total capacitance available to the circuit. Sorry, connect them in series. Whenever we connect capacitors in series, then that results in an overall reduction in the total capacitance in the circuit, as opposed to connecting them in parallel where the capacitance is added, and therefore we increase the capacitance available to the circuit by connecting capacitors in series. Good? For part D, what we're asked to find is the total energy stored in the circuit. So what we've calculated thus far, we have the battery voltage, 50 volts, which of course is the total PV across all the capacitances in the circuit. And we've also managed to calculate the total capacitance in the circuit. So since you have the total PD and you have the total capacitance, we can say that the energy stored, W, is equal to a half CT, say VT squared. Where of course VT would be the total PD or the battery EMF, right? So we can just write it as that. So this gives us a half 18 microfarads times 50 squared, right? So this gives us, well, a half times 18 microfarads times 2500, and this is supposed to give us approximately 0.0225 joules. All right, so the total amount of energy stored is 0.0225 joules. Right, so that was question 3 from our worksheet. Now, let's look at question 4. Question 4 says a 500 watt flash lamp fitted to a camera operates when a 5000 microfarad capacitor discharges through the lamp. The capacitor charges from a 9 volt battery. Calculate the energy stored in the capacitor. So in this question, we're given the power of the lamp, 500 watts, right? But we're not given any time. It's fitted to a camera and it operates when a 5000 microfarad capacitor discharges through the lamp. So the capacitance of the capacitor C is equal to 5000 microfarads. And it discharges, the capacitor basically charges from a 9 volt battery. So therefore V is equal to 9 volts. And they want us to find the energy stored in the capacitor. So the formula is simple, straightforward. W is equal to a half CV squared. So this gives us a half times 5000 microfarads times 9 squared. And this gives us approximately 0.203 or exactly 0.2025 joules. So the exact value of the energy stored by this capacitor is 0.2025 joules. Alright, so that was number 4. Number 5 says, if all the energy stored by a 250 microfarad capacitor charged to a PD of 7500 volts could be used to lift a man of mass 75 kilograms, what would be the greatest vertical height through which he could be raised? Of course, you assume to be used gravitational field strength as 10 newtons per kilogram. So first of all, what is going to happen is that the capacitor will store a certain amount of electrical energy. And then, of course, this electrical energy will be used to raise the man through a particular height, which therefore means that this electrical energy will be converted to gravitational potential energy, right? So we can say that, assuming energy is conserved, so assuming energy is conserved, loss of electrical energy is equal to the gain of gravitational potential energy. Now for the capacitor, we're given its capacitance as well as its voltage, and therefore the formula for the energy stored is given by a half CV squared, and the gravitational potential energy is of course given by mgh. So basically substitute values into the equation and we then solve for the height h. So substituting, we get that right. So the capacitance 250 microfarads, we convert that, so half 250 microfarads, same thing as 2.5 times 10 to the minus 4 farads. And the voltage is 7,500, so that's times 7,500 squared. And this will be equal to the mass of the man, which is 75 kilograms, times G, which for simplicity we're using as 10, times height h, right? And the only unknown in the equation is h, and this should work out to give a height of 9.375 meters. So from this we should get h is equal to 9.375 meters. Right? Just check our value. So we have 2.5 exponential negative 4 times 7,500 squared times 0.5, and you then divide it by 750, right? So 9.375 meters. So that is the height through which the man of mass 75 kilograms could be raised by a capacitor, which basically would have stored this amount of electrical energy, or which would have been charged to a capacitance of capacitor 250 microfarads, which would have been charged to a PD of 7,500 volts. Right? Good. That was number 5. Now let's look at number 6. Right? So this was number 4. This is number 5. Let's now look at number 6. Number 6 says a 5 microfarad capacitor is charged to a PD of 10 volts. It is then removed from the supply and connected in parallel with an uncharged 20 microfarad capacitor. Calculate A, the charge on each capacitor after the connection. So initially we have a 5 microfarad capacitor which was charged to a PD of 10 volts, right? And then that capacitor will then be removed and connected across an initially uncharged capacitor of capacitance 20 microfarads. So after that has taken place, we have something circuit looking something like this. Right? So we have a 5 microfarad capacitor, 20 microfarad capacitor. Now because this 5 microfarad capacitor was initially charged, when it is connected across initially uncharged 24 microfarad capacitor, it will basically discharge across it, and essentially the 20 microfarad capacitor will become charged, and the 5 microfarad capacitor will lose some of its charge, but the 20 microfarad capacitor will gain that amount of charge. And we say that the total charge is conserved. So whatever charge the 5 microfarad capacitor initially stored, that total charge remain constant, but of course it will now be redistributed between the two capacitors. And because of course they're connected in parallel, eventually the PD across them will be the same. Right? Now let's first go ahead and find the initial charge stored by the 5 microfarad capacitor. So this will be given by CV, which of course is 5 microfarads times 10 volts, which gives us 50 microcoulombs, or 5 times 10 to the minus 5 coulombs. So this will be the initial charge stored by the 5 microfarad capacitor. Good? Now, what they really want us to do, however, is to find the charge stored on each capacitor after connection. Now, we know the total amount of charge stored by the 5 microfarad capacitor. We're not given any voltages yet, right? But what we need to find is the charge stored on each capacitor. Now, basically, whenever capacitors are connected in parallel, the ratio of the charges stored will be in the ratio of their capacitances. What exactly does this mean? If we have two capacitors of capacitance C1 and C2 connected in parallel, right? So let's say, for instance, C1 and C2 connected in parallel, the ratio of their capacitances will be equal to the ratio of the respective charges stored. So in other words, then we can say that, well, C1 over C2 will be equal to Q1 over Q2, because the ratio of the capacitances will be equal to the ratio of the charges stored. So what this basically means is that if we have a capacitor of capacitance 5 microfarads and 20 microfarads connected in parallel, then these would basically be in the ratio 5 to 20, same thing as 1 to 4. And therefore, the charge stored will be in the ratio 5 to 20 or 1 to 4, right? So therefore, what this means is that, so we can say that C1 to C2 would be equal to 5 to 20, which of course, if we simplify, that gives us the ratio 1 to 4. So therefore, the charges stored will also be in the ratio 1 to 4, which means that basically the smaller capacitor will store 1/5 of the total charge, and the larger capacitance will store 4/5 of the total charge. So therefore, this means that for the 5 microfarad capacitor, then the charge stored is equal to 1/5 of 50 microcoulombs, which gives us 10 microcoulombs. And for the 20 microfarad capacitor, the charge stored Q, let's call it Q1, Q2 will be equal to 4/5 of the total charge stored, which gives us 40 microcoulombs. So therefore, what this means is that the 5 microfarad capacitor, after discharging across the 20 microfarad capacitor, will only store a quarter of the charge, a fifth of the charge, whereas the 20 microfarad capacitor will store 4/5 of the charge that was initially stored by the 5 microfarad capacitor. And of course, 10 microcoulombs, same thing as 1 times 10 to the minus 5 coulombs, and 40 microcoulombs, same thing as 4 times 10 to the minus 5 coulombs. Part B of the question wants us now to find the total capacitance of the combination, but that part is relatively straightforward. Because the capacitances are connected in parallel, then the total capacitance is simply the sum of the individual capacitances. So for this particular case, same question 6, part C, the total capacitance CT is equal to C1 plus C2, which gives us 5 microfarads plus 20 microfarads, which gives us 25 microfarads. So the total capacitance is 25 microfarads. Good? And lastly, they want us to find now the PD across the capacitors. Now, what information do we have in order to calculate the PD? We have the total charge stored, which is 50 microcoulombs, and of course, we have the total capacitance. So therefore, the total charge, QT, equals 50 microcoulombs, and we know that Q is equal to CV, which therefore means that V is equal to Q over C. So therefore, the PD, V, across the plates of the capacitor will be equal to the total charge stored divided by the total capacitance, which gives us 50 microcoulombs divided by 25 microfarads, and this gives us 2 volts. So after discharging across the initially uncharged capacitor, the PD across the plates of each capacitor has now fallen to 2 volts. All right, that was question 6. We'll then go on to question 7. Alright, so question 7 says, calculate the energy stored in a 20 microfarad capacitor when charged to a PD of 500 volts. If a second initially uncharged 30 microfarad capacitor is then connected in parallel with it, calculate the new value of the energy stored by the combination, account for this change. So what we have initially is we have an initially a 20 microfarad capacitor. So we have C equals 20 microfarads, and it was charged to a PD of 500 volts. V is equal to 500 volts. And therefore the initial energy stored, let's call that W, right? So the initial energy stored, W naught, is equal to a half CV naught squared, right? So since the initial energy, we use the subscript 0, right? So initial energy stored. So W naught is equal to a half CV squared. So this gives us a half 20 microfarads times 500 squared, and this gives us, this should give us 2.5 joules. So the initial energy stored is 2.5 joules. Now the next part of the question tells us that this capacitor is now going to be connected across an initially uncharged 30 microfarad capacitor, right? So what is happening now is that we have a 20 microfarad capacitor connected across, that is in parallel with a 30 microfarad capacitor. So this one is the 20 microfarad capacitor, and this is the 30 microfarad capacitor. And they want us now to find the total energy stored after this connection is made. So first of all, because they're connected in parallel, the total capacitance, CT, is simply equal to the sum of the capacitances. So 20 plus 30, that gives us 50 microfarads. Now, before we can actually proceed to find the energy, we need to find the final PD across the plates of these capacitors. Now, how do we go about doing that? We can go back to the initial information that we're given. We can then find the total charge stored, then find the charge stored on each capacitor, or we don't need to do that, sorry. We can find the total charge stored, and since we know the total capacitance, we can find the PD across the plates of each capacitor. Actually, we don't need that either. We can find the total charge stored, and since of course charge is conserved, we can then use that now to find the total energy, right? Energy stored. So going back here, the total charge stored, let's call it Q naught, is equal to C V naught, right? And so this gives us 20 microfarads times 500 volts. 20 times that gives us 10,000 microcoulombs, or this is the same thing as 1.0 times 10 to the, is that minus 2 coulombs. Right, or 0.01, right? Same thing as 0.01 coulombs, right? And so that is the initial charge stored. Now, when these two capacitors are connected in parallel, the charge will be conserved. So the total charge that was stored on the one capacitor will now be stored in total by the two capacitors. So this is still going to be the total charge stored. And now that we found the total capacitance CT, we can then find the total energy stored, right? This time, however, we're not going to be able to use this formula because obviously we don't have the PD. However, we have other formulas we can use to find the total energy stored, and that formula is given by W is equal to a half Q squared over C. Right? So the total energy stored is given by the formula a half Q squared over C. And so we have W is equal to a half 0.01 squared divided by the total capacitance, which is 50 microfarads, or 5.0 times 10 to the minus 5. And what does that give us? We have W equals, now that should give us 1 joule. Well, let me just check. We have 0.01 squared, 0.01 squared divided by 5 exponential negative, this is negative 5, negative 5. Right, times 0.5, that gives us 1 joule. So after the two capacitors are connected in parallel, the initially uncharged capacitor will acquire some amount of charge, as the initially charged capacitor, the 20 microfarad capacitor, will discharge across it. Now, during this discharge, of course, energy will be dissipated as heat in the connecting wires in the circuit, and therefore this is where this extra 1.5 joules of energy that was initially stored would have gone. So we see that basically more than half, approximately 60%, 1.5, 3/5. Approximately 60% of the initial energy that was stored has essentially been dissipated as heat due to the connecting wires in the circuit, right? And that was basically, that was question 7. Now let's look at number 8. Number 8 says a 4 microfarad capacitor is charged from a 12-volt battery. So let's write down the information that we have. It is a 4 microfarad capacitor. So C equals 4 microfarads. It is charged from a 12-volt battery. So the PD of the battery, or the EMF E of the battery, is equal to 12 volts, right? And then discharged through a 0.4 mega ohm resistor. So the resistance R is equal to 0.4 mega ohms, right? Calculate the initial charge stored in the capacitor and the charge on PD and charge on and PD across the capacitor 2 seconds after it starts to discharge. So let's look at this. So we have the battery EMF, which is 12 volts, and we have the capacitance of the capacitor. Now, generally, if a capacitor is charged by a particular battery, after it's fully charged, the PD across the plates of the capacitor will be approximately equal to the battery's EMF. So therefore, to find the initial charge stored in the capacitor, A, we can say that Q naught is equal to C E, where E, of course, is the battery's EMF, right? Or if we want to call this V naught, Q is equal to C V naught, where, of course, V naught would be equal to the battery's EMF. And so therefore we see that Q naught is equal to 4 microfarads times 12 volts, which gives us 48 microcoulombs, or 4.8 times 10 to the minus 5 coulombs. So 4.8 times 10 to the minus 5 coulombs, right? That is the initial charge stored. Now, the next part of the question wants us to find the charge on and the PD across the capacitor 2 seconds after it starts to discharge. Now, whenever we have a discharging capacitor, the discharging equation relating current, voltage, or current, it takes the form X equals X naught E to the minus T over CR, where X naught, of course, is a particular value at time T equals 0, and of course X is a value at time T. So in this particular case, well, X could be either current, voltage, or charge. But in this particular case, we're asked to find the charge stored and the PD across the capacitor 2 seconds after it starts to discharge. So to find the charge stored 2 seconds after, the formula basically is Q equals Q naught E to the minus T over CR. Now CR, the product CR, of course, is a product of the capacitor's capacitance and the resistance of the resistor, and is known to be the time constant of the circuit, right? So we can find the value of CR. So CR would be equal to 4 microfarads times 0.4 mega ohms. Prefix micro is 10 to the minus 6. So this is 4 times 10 to the minus 6 farads times 0.4 times 10 to the 6 ohms. So the 10 to the 6 and the 10 to the minus 6 basically multiply to give 1. And then we have 4 times 0.4, that gives us 1.6. And this will be seconds. So therefore the time constant of this capacitive circuit, or this circuit, will be 1.6 seconds. Right? Having worked that out, we can then plug it into our equation now to find the PD after 2 seconds. Right? So we can now use our equation. Q equals Q naught e to the minus t over CR, where of course E is the numerical constant having the value approximately 2.718, right? So whenever we take natural logs, we normally take logs to base E, that's E, right? So substituting these values now, we get that Q equals 4.8 times 10 to the minus 5 times E to the minus 2 over 1.6. So this becomes Q equals 4.8 times 10 to the minus 5 times E to the minus 1.25. And this gives us 13.8 microcoulombs, or 1.38 times 10 to the minus 5 coulombs. So the charge stored on the capacitor after 2 seconds is 1.38 times 10 to the minus 5 coulombs. And of course, since the capacitance remains constant, we can now say Q is equal to CV, which therefore means that V is equal to Q over C. So therefore, V is equal to 1.38 times 10 to the minus 5 coulombs divided by the capacitance, which is 4 times 10 to the minus 6 farads. And this basically gives us 3.44 volts. Right? So after 2 seconds, the charge initially stored in the capacitor has fallen from 48 microcoulombs, or 4.8 times 10 to the minus 5 coulombs, to 13.8 microcoulombs, or 1.38 times 10 to the minus 5 coulombs. And the PD across the plates of the capacitor has fallen from 12 volts to a value of 3.44 volts.